You clicked because you want to understand GPU specs for AI inference, but here is the hard truth. Raw floating point operations per second will mislead you into buying hardware that cannot run your model at all. The real problem is that consumer-grade graphics cards lack the memory bandwidth and unified capacity required to hold large language models during actual deployment. By the end of this video, you will know exactly why adding more accelerators often makes performance worse instead of better, and what architectural shifts are actually needed for production success. Let us start with a common assumption that many engineers make when they look at spec sheets. They see a consumer GPU boasting high theoretical compute power in teraflops or petaflops and assume it is ready for large language model inference. This belief drives purchasing decisions across the industry, yet empirical data reveals this logic is fundamentally flawed. The bottleneck shifts from raw calculation speed to memory bandwidth as soon as you attempt to load complex models into system RAM. Consumer cards prioritize compute density but suffer critically low throughput when accessing vast amounts of weight parameters required for generation tasks. Consider what happens inside a large language model during inference. Every token generated requires the system to retrieve specific weights and perform matrix multiplications across billions of data points simultaneously. If your memory subsystem cannot feed those numbers fast enough, the powerful processor sits idle waiting for data. This is where high-bandwidth memory becomes the critical differentiator between a working deployment and a stalled process. Datacenter accelerators utilize HBM stacks specifically designed to match compute intensity with massive throughput, whereas consumer cards rely on standard GDDR memory that simply cannot sustain the required flow rates at scale. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The consequences of ignoring this mismatch become apparent when teams attempt to deploy models using naive scaling strategies. Research into large-scale training clusters reveals a stark reality about how efficiency degrades as you add more nodes. When organizations try to use fully sharded data parallelism on massive hardware farms without optimizing for memory constraints, they encounter prohibitive communication overhead. Empirical studies show that beyond roughly 32 high-end accelerators in a cluster, the power consumed by data movement eclipses any computational gains from adding another card. This creates a scenario where you spend more energy moving weights between chips than actually processing them, leading to over 30% inefficiency compared to optimized single-node strategies. This phenomenon challenges the prevailing "more is better" hardware mindset that dominates current engineering discussions. Adding accelerators yields diminishing returns rather than linear performance growth if your system architecture does not align with physical constraints of memory access patterns and network topologies. The interconnect bandwidth required for distributed training across thousands of nodes becomes a hard ceiling where communication delays dominate the execution timeline. Consequently, naive scale-out approaches often fail to deliver stability at extreme scales because the fabric connecting the hardware cannot keep pace with the demand for parameter synchronization. To overcome these physical limitations, successful deployment requires rigorous model, hardware co-design rather than relying solely on raw compute power available in any modern chip. Architects must rethink how models are structured to fit within memory capacity limits and bandwidth constraints that cause systems to fail when scaling beyond specific hardware thresholds. One promising approach involves mixture of experts, architectures which activate only a subset of parameters for each query, drastically reducing the active memory footprint required during inference. Another technique is multi-head latent attention, designed specifically to mitigate memory access latency by compressing context representations before they reach the compute units. These architectural innovations allow systems to operate efficiently even when constrained by finite HBM capacity or network bandwidth limitations. By aligning algorithmic design with physical hardware realities, engineers can achieve performance gains that raw flops alone could never predict. The shift from brute force computation to intelligent data movement represents a fundamental change in how we approach artificial intelligence infrastructure. It moves the focus from what your processor can calculate to how quickly it can access the information needed for those calculations. However, there is still an open question regarding smaller clusters where consumer GPUs might suffice for specific parameter ranges. The bottleneck threshold appears to vary significantly depending on model size and complexity. For models with fewer parameters or simpler architectures, standard memory bandwidth may remain adequate without requiring specialized enterprise silicon. This suggests that while data center accelerators are essential for massive scale, entry-level hardware could still be viable in niche applications where communication overhead remains low and weight storage fits within consumer limits. Furthermore, emerging solutions like Dynaflow demonstrate how dynamic scheduling can mitigate static hardware inefficiencies by adapting resource allocation based on real-time workload demands. Yet the literature leaves a knowledge gap regarding its real-world adoption rates and cost-benefit analysis compared to specialized enterprise silicon. We do not yet have comprehensive data comparing these adaptive approaches against traditional fixed configurations in production environments across diverse use cases. The industry continues to evolve as new techniques emerge, but current evidence strongly supports prioritizing memory optimization over raw compute expansion for most large-scale deployments. The takeaway is clear. If you are planning a production deployment of any significant scale, do not let theoretical flops numbers dictate your hardware strategy. Instead, evaluate the memory bandwidth and HBM utilization capabilities relative to your model's weight size and attention mechanisms. Success depends on designing systems where data flow matches computational demand rather than hoping that more processors will solve every bottleneck. Without optimizing these fundamental access patterns, you risk building infrastructure that is expensive but ultimately ineffective for running the models it was designed to support. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.